In this lesson, we're going to look at how to perform linear regressions by hand mathematically, but then also by using electronic software like Desmos, our free graphing calculator. So first of all, let's begin with what linear regression is. It's a way of finding the best fit line between a two-variable data set, between an independent and a dependent variable. The best thing about a best fit line is it also allows us to make predictions within the data set as well, both within the data set and outside of it. So in other words, if I were to, at this point in my skill set, estimate where the best fit line is, I might try and connect, as many points as I can while having an equal number above and below the line. And maybe something like this would work, where I've got 4 points above, 4 points below, kind of spread out, and I'm able to connect 3 of them. Okay. If I want to draw in that best fit line, yours and mine might differ a little bit because we're using our best estimation skills to create it. However, we can still use that line, even with our limited skill set at this point, to make predictions within this set. So if the line goes through here, maybe I want to know, hey, a grade 12 student with an average of, say, 83. There's no exact data point for that, but I can use the best fit line to then predict what their first year average would be at a post-secondary institution. This is called interpolation because it's making predictions within the lowest to highest set of data. If I want to do extrapolation, that would be going beyond the data, so up in this region here or down in here. So maybe something lower than 75, and then maybe something also higher than, say, 95. Maybe someone who has 99 I'd want to predict as well. So that's interpolation and extrapolation. So if I said to you right now, plot the data, draw the line of best fit, and find the equation, you would do as I did and estimate what that best fit line would look like, and then we would want to concretely come up with its equation. We need to find its slope, and we would need to find its b value. We always find slope first and then find b after the fact. So what you would do is you find 2 points that are perfect points along your best fit line, ones that cross along the corners of the grid line so that you could read the coordinates accurately. You might calculate slope using y2 minus y1 over x2 minus x1, where this is one of the data points that's on your best fit line, and here's another point that's on your best fit line. And you would find an answer for slope that you could then put into the equation. To find b, you wouldn't be able to get it from this particular graph because I would predict that my best fit line, well, it might here, but I don't think it would. I think it would go below my x-axis and I'd really be estimating it. So what I can do instead is I know that if I rearrange y equals mx plus b, I can say b equals y minus mx. I could sub in my slope value that I calculated here, and then I could use one of my perfect points up here to sub in, or any other perfect point for that matter, as long as it's on the line, to find a b value, which could then go into the equation here. And that's how you would find the equation of your best fit line. However, what if there's a way to be more accurate with this than just eyeballing a line and eyeballing some best fit points and making some rough calculations? What if we could do better? And the answer is we can. We can using something called a least squares method. What the least squares method does is it says this best fit line should have points that are equally above it and equally below it, so much that these differences between the heights of the points above and the differences in the heights of those below should cancel each other out. These are called positive residuals if they're above and negative residuals if they are below. Anyways, someone has done some fantastic work for us to derive an equation that could actually calculate what m should be for the best fit line and what b should be for the best fit line using the data itself. So on page 2 of your note, let's explore what that looks like. So here I have on page 2 the data with x again listed in the first column, y in the second. And what we're going to do is we're going to use this equation, the least squares method way of finding the slope of the best fit line. Now again, it looks like a little bit of a mess, and you'll notice that it has a lot of summations in it. And one of the easiest ways we could create values for those summations is to set up a chart like this, kind of like we did in the previous lesson. So if we go ahead and fill this in, we notice that the sum of all the x values comes out to 844. And the sum of the y values comes out to 761. Now you should go ahead and you should do the x squared values, so square 85, put it here, square 90, and so on, and add them all up to make sure that you can do it. Because watching me do it is easy, but I had to do it in order to get this answer too. So what value do I get for all of the sum of the x squared values? Well, I get 71,598, and I hope that you do too. And again, you should do it, check to make sure that you do. Let's do the same thing for the square of the y values. So the square of the y values, the sum of the squares of the y values is equal to 58,555, according to my calculations. And the sum of the x times y values for each of these points comes out to 64,654. So now it's time to plug these in to where we can in this equation. Now the only one you'll notice that's missing in here is the sum of the y's, but we'll come back to that one in just a moment. We also notice that n appears in this equation again. N is the total number of data points that you have, which is 10 in this case. So let's plug in some values. We have an n value of 10. We have a sum of x times y values of 64,654. From that, we're going to subtract the product of the sum of the x's and the sum of the y's. So, y is right there. So we're going to put in 844 for the sum of the x's. We're going to put in 761 for the sum of the y's. And then on the bottom, we have the sum of the x squareds times the number of data points, so 10 times our green value here. And from that we subtract the sum of the x's quantity squared. That's our pink value. So 844 quantity squared. All right, in your calculator you can do this all at once, but you should use brackets around the numerator, brackets around the denominator so that the division gets done properly for the simplification of each of those places. Or you could do the numerator separately, the denominator separately, and then do the division at the end. And you'll find that it comes out to being approximately 1.17. All right. Next, we need to find the b value for our line of best fit. Now, when we're using the method of least squares, instead of putting in any old point, because we don't know any points on this line, we haven't drawn it, we're not reading them off a graph, instead what we're going to use is we're going to use the mean value of the x's and the mean value of the y's. So that means we can take the sum of all of the x's, which is 844, and divide them by the number of data points, which is 10. And we'll discover that the mean value comes out to 84.4. We can do the same thing for the sum of the y's. We have 761, but if we want to find the mean of that sum, we add them all up like we did here and divide by the number of data points, which is 10, so that we end up with a y mean of 76.1. So let's use these values now to find the b value for our equation of line of best fit. So, subbing in the mean of the y's gives 76.1 minus our slope, which is 1.17. And while you have this in your calculator, it's best to leave this with all of its decimals, even though we've approximated here on paper, to give the best b value possible, because the more we round in each of our calculations, the more off our final answer will be. Our x value here is 84.4, and when we punch this in, we get a b value of negative 22.65. Okay? So what that would mean then, if we put these two pieces together, is we can say with certainty, therefore, the equation of the line of best fit for our data set is y equals mx plus b, 1.17x. Our b value is negative, so subtract 22.5, or sorry, 22.65. And that's a much better value than what we would get if we had gone back to our original graph, drawn in what we thought was the best, tried to estimate some points. This is a lot more accurate to more decimal places. In the next video, we'll look at how to do all this with our good friend, Desmond.